Yes.
Good, perfect. So let's start then. So does anyone have any questions from yesterday, maybe? Okay, so yes, so Zung, she said some problem. She said that she has some problems with the installation of OpSpy. So after the lecture today, I will show her how to install this. We will go through her installation on the Windows. So if someone else has any problems, you can stay online and we go through it together. So
Okay,
everything works as it should. So okay, today first I will show you some slides. We will look at the some very simple methods for earthquake detection, and we will talk something about the earthquake location. And then we will go through some more Jupyter notebooks. Actually, no, sorry. We have to, let me stop this. I still have, where is my, actually, there are some more from yesterday we did not finish completely. So let me share this screen. Oops. Share this on Safari. Share. So what do you see now?
Yeah, I see the waveform for Sumatra.
Ah, okay, okay. So you see, because there is no, it doesn't, Zoom does not say that, okay, so everything works. You see the waveforms, good. Okay, so yesterday, at the end of the lecture, we looked at these instrumental responses. How does this work and what it actually does? And now let's look at the last few basic pre-processing steps that you have to do quite a lot. So let's first look at the filtering of the data. So by doing some simple filtering, we can increase the signal to noise ratio for some frequencies that we are interested. So let's say the signal to noise ratio, what this means is, let's say in this example here, this is the noise, a very small signal, and this is our signal that we are interested in. And if the signal to noise ratio is high, it means that our signal is really well visible on the waveform. While if the signal to noise ratio is low, then the signal, I mean, the noise is so high that we can barely see an earthquake on the waveform. So let's say for earthquakes, what we are interested in, so as I said yesterday, somewhere in this range or slightly lower even. At low frequencies, we will see, let's say, surface waves and long period waves, while at higher frequencies, up to around 50 hertz, we will see body waves arriving to our station. Then we have these normal modes that you can also see here a few days after the Sumatra earthquake. These are very, very low frequencies. So this is where you should study them. So now we will look at some different filters, how easy it is to filter the data with the OpSpy and what this actually does. So let's first download one big earthquake from New Zealand. This is a magnitude around 7 earthquake that happened in 2016. I will download this. So here on this figure now, you see what this is, few minutes of data. And you can see here at the beginning where the signal starts, We have a very, very high frequency body waves arriving, P and all the reflected P's. You see these frequencies are very, I mean, the wiggles are very close by. And then after some minutes, very large surface waves arrive. And these are long period waves, as you can see here. So we can check this frequency content of the data we are looking at either in this time series, but this is not very, you will not see much here, or you can generate this so-called spectrograms, where you take a trace that you're interested in and call the spectrogram method on it. This dB scale, this just changes the scale of what you are looking at. You can play with this to see, sometimes you better see the signal you're interested if you set this to true, sometimes not. And this CMAP is just a color scale we will use. This one here is called plasma. So when I run this, you can see the earthquake here. Maybe let me change this to something better. This is the first one that I remembered. Okay, maybe this is better viewed now. So you can see this at the beginning. You see kind of high frequency. Let me maybe change it to logarithm. It's not better. So you can see that we have some high frequency signal at the beginning, which corresponds to this P wave. And then this high frequency is going down. So the majority of the signal is within the low frequency. And at the same time, you can see these very narrow spikes. These are local earthquakes. So small earthquakes that happened close to this station and has a very high frequency. So why it looks like this? Because as you know, the high frequency attenuates very fast. So if your station is close by to the earthquake, you will see all these high frequencies. If it's not close to the earthquake, you will see lower frequencies. And for the large earthquakes, of course, the presence of low long period wave is dominant. Okay, so now let's say that we are only interested in these high frequency earthquakes here. We can do some filtering. We can call this filter method that you see here on the stream or the trace object. And okay, so let's say if we want to, let's do it first like this. Let's just look at the high pass filter. So what this filter does, it removes everything beneath the frequency that we set here. So in our case, 2. So let's make so this is, you see, this is the same signal as here, but you only see the high frequency content. Let me try to plot them one by one. Oh no, this is wrong. This one. Like this. Yes, okay. So you see, it starts at the same time, but because we are only looking at the high frequency earthquake, the signal will look slightly different, especially at the coda part where our long period waves now are removed. And now here you can see these local small earthquakes that before you were not able to see here. And this is the, okay, this does not look so nice anymore. Let me change back to what it was before, plasma, okay. Now you can see that, okay, we don't have this low frequency noise that we have here. We don't have it anymore, and we can really see these small aftershocks. So what we can do also, yes. Just a second. What I wanted to say here. Okay. Oh, okay, yeah. If we compare to the main shock here with low frequencies, this is some aftershock that has, you know, many more of these small wiggles. The time scale is not exactly the same, but okay, it's not so important. So now, if we are only interested in low period signal, so let me make these two here. So let's say we are only interested in the long period waves. We can use the low pass filter, which will only contain the frequencies below something that we set. So this is 0.25 hertz. So we can plot this. So this is the original signal. This is the high frequency signal. And this is now just the low frequency. We can go even, let's say, lower. You can see now we only look at the low frequency content of the data. So you see there is a big difference in this raw recording, the high frequency and low frequency. And you see that local earthquakes are only visible on the high pass filter. Then the third filter, which is commonly used, is, let me just copy this. It's called band pass filter. So we define it like this. So in this case, what happens is if we select the band pass filter, we let only the frequency of some band through our filter. So let's say we only want to see frequencies between 5 and 10 hertz. Okay, now let's plot these few signals and compare them. So let's remove this and see. Yeah. So you see the differences, the raw, everything above 2 hertz, everything below 0.05 hertz, and everything between 5 and 10 hertz. So you see that by doing this band pass filter, we really can highlight the aftershock sequence. We can maybe even change it a bit more. Normally it should be something, let's say, let's check here. You see now these are really popping up. Okay, and then the last commonly used function is this resampling. So again, this is our original signal, and we can resample our data, let's say, to 0.1 second. So basically, this will downsample our data very, very strongly. So you see now that our data only has 0.1. Every 0.1 second we have a measurement. No, sorry, every 10 seconds we have one measurement. So the sampling rate here is very, very low. You can see this. And let's say old seismic stations, recording of very old seismic stations would, let's say, look something like this, while modern would look something like this. And then, yes, also the trimming. So if you want to cut the data, you want to just use a small part. So we take our original data and we call this trim function. So trim, and in the first place, we put the start time of cutting, and on the second place, we put the end time of the cutting. And let's say in this time, we only want to look at the P wave and the P wave coda, so just this small time window here. and it looks like this. You see this second plot is just the P wave window. You can see that it starts to have a high frequency and also this low frequency period. And so this is this small part. Okay, so does anyone have any questions here?
Hello?
Yes.
I wanted to know, first of all, it's like for the trim function.
Mm-hmm.
So you just used the function, and the parameter of the function are the date. And here I see that the date is almost the same.
Yes,
so we have
it's only so it's only what this is a month, this is hour, minute. So in this second plot I only show 25 seconds of data. This is the original, which is a few minutes long. And here I specify that I want to cut only this very small amount of data. So this is it.
Okay.
But
and
you
the other, yeah.
No, please.
I don't understand. I mean the y-axis. What does it represent?
The y-axis.
Yeah.
So okay, this is because this is raw data. We have now counts versus time. So here, yeah, count. This is a raw data recording. Is let me go up here. Yes, so the raw data is recorded. You see here, it says counts.
Okay. It's okay.
Yeah. These are this digital unit.
Since
which,
is digitals. Okay.
Yeah. So this is something, without any physical meaning. That's why.
Okay.
That's why when you work with the data, you need to normally change. You have to remove the response to go from this digital to the let's say in our case meters per second.
Okay. Thank you.
Because then in this case, if I remove the response, we can do it. I mean, and we'll see how this will change. Just a second. Let's do this here. No, I have to use the name of the. Where is this? Maybe it will be here. Oh, this is different network. Okay, I will download the instrumental response. So which station is this? Viz NS. So NZ Viz station. This let's put here. Response, everything. I need to. What is wrong now? GeoNet. Oh. Okay, I don't know exactly now what I have to change to get this data. Let's see, maybe GeoNet. I use this network NS. Okay, but what I can do is better. Okay, yes. You can, when you download the data, you can already attach the response. So now this should work. I can delete this and just remove response. Okay. Now you see this changed. Before it was few thousand something, but now this is in meter per second. So if we, yes, look, I can do it again without the removed response. You see, this is 60,000. But if I remove the response, I go to 0.00012 meter per second for the first waves. But if we look at the later arrivals, so let's put here 10. So you see also the strong, you see this is 0.015 meter per second velocity.
Yes, yes.
We
Thank
can
you.
change to, call it, I forgot. And I can put it to anyway, you can change to acceleration or to displacement, and it will be according to these values. I mean, these values will change. Okay, so, and something else?
Okay, thank you.
Okay, so this remove response, as I said, you do this when you are working on some problem that needs physical values. Let's say for earthquake detection and phase picking, if you want to put P and S arrival times, you don't have to do this because you are interested in raw recording. Okay, so this is it then. If no one has any questions on this talk, I will close it. Now we will, yes, let me open now the PowerPoint that I have. Okay. So you see the PowerPoint?
Yes.
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 Okay, so
Yes.
I will talk now a bit about how we can detect the simplest ways how to detect earthquakes and how to locate them. So I will explain some very simple algorithms, and then if we have time during this week, we will try to also implement one of these algorithms for detection of earthquakes. So you will see that this is actually very easy. So first, we will talk about some of the errors that we might come up doing this kind of work. Then we will look at the most used algorithms. Then we will talk about one very interesting algorithm for detection of similar earthquakes. So let's say if sometimes you have earthquakes that their waveform is almost identical, and we will talk about this. We will talk about location of the earthquakes, so about absolute location and relative earthquake locations. And at the end, I will show you a few examples of works that used match filter detection algorithm, the one for looking of similar earthquakes, and why this is important. So, okay, first, let's first talk about errors. So there is multiple sources of errors, and one of the most, that one that you need to consider the most is the network geometry. So on this picture, you see the yellow triangles are permanent seismic stations running here in this part of Europe. You can see that some areas are very dense. So Italy, Switzerland, Germany, Austria. Well, it depends. This part of Italy, the stations are very dense. This part of France, stations are very dense. This part of Switzerland, and for the last few years, this part of Italy, extremely dense. and also Slovenia. This is because we are in area of Alps, so a lot of earthquakes happen here, and we are interested in this since quite some time. But then you have Austria, Germany, where not so many earthquakes happen, or let's say countries that are not very rich. Bosnia, here you see only a few stations, even though earthquakes are very common here. So you can see how different density of networks are available. Let's say yesterday when we look at Ghana, only few stations were there, so you have some idea.
Yes. Yeah,
So
we have few workshops, so that's why.
okay. As long as you can do something with them, this is already something interesting.
Yes.
Yes, and then we have, these projects, big project. This is called Alp Array, where they put many stations for, I think, 2 or 3 years. Temporal stations which are measuring noise, earthquakes, and everything we want here in this part of the Alps now. So, yes, in the past also the equipment was very expensive, so not many stations were available. And as I said, yes, the developing countries also suffer quite a lot here. So the problem now here with our stations is if we don't have enough, this will limit our magnitude of completeness of the catalog. So this means that instead of magnitude of completeness means that, let's say, if magnitude of completeness is 2, this means that in our catalog we will have all earthquakes with magnitude 2 and above. While if your stations are not dense enough, normally the magnitude of completeness is around 4. And also if the geometry of the network is not good, we will get big errors in the location of the earthquake. Another problem, let's say, if we just consider these red stations here, the network is very dense. So if earthquake happens here in the middle of the network, we will get very good good quality location. But if the earthquake happens, let's say, somewhere on the edge of the network, and we do not consider this, but only the red ones, our location will not be good anymore. So as soon as we put our earthquakes on the edge or outside of our network, the errors become bigger. So the main contributors to the error of the network configuration are, of course, the distance between stations. This is because for accurate depth estimation, we have to have a closest station to the earthquake, which is not further away than the depth of the event. So if our earthquake happens at the depth of 10 kilometers, the closest station should not be further away than 10 kilometers. Otherwise, the problem becomes a bit unstable, and the depth error can be quite big. Also, let's say small earthquakes, if we don't have a very dense network, cannot be really well located due to the magnitude, and because the waves then do not travel very far away, and also because small local earthquakes will normally have a high frequency content that in majority of the cases will dissipate very fast. So we will not see this high frequency shaking very far away. And then the other one is geometry, like I said before. So let's say if we look at this very extremely simple case, which, it's not really the case, but just to get some idea, if we have 3 stations and we make these circles around them, so the D1, D2, D3, this is the radius of the circle, and this can be, very easily computed if you take the S phase arrival minus P phase arrival on your station times 8, and you get this distance, and you can make these circles around each station, and where these circles meet, this is the epicenter of our earthquake. Now, this is if you have 3 stations, but if you have 2 stations, suddenly you get 2 crossings, right? So you don't actually know which one is correct one. So, you know, more stations you have, closer they are in space, better constrained location we will have for the earthquake.
Please, Professor,
Mm-hmm.
why times 8 and times 10?
Yes, this is depends. You see, depends on which phase you use. This is SG and this is SN. So one is a direct, one is reflected. So with this one you get epicenter. With this one you can also kind of get a hypocenter, so also some depth information. But this is not used. I mean, this is just first. I mean, this is how they started. You know, ages ago. Today we use much more complicated algorithms. So this is, you know, just let's say if you want to tell someone how this works, a very simplified way is to do this calculation.
Please.
Mm-hmm.
So it means the installation of the stations. If you want to install, like for example, in Ghana, we have only few stations.
Yes.
And if I want to install the station, I should like specifically install them at where I think maybe there is some fault that can cause an earthquake or something. Or
yes, of course. I mean, the problem is that, let's say, if you want really high quality professional seismic stations, they cost a lot, really huge amount of money. So if, okay, let's say we want this. And if we want this, then we can only afford few of them. So the best way is, yes, of course, to install them close to the areas where we expect earthquakes. Then the next problem here is that, so we limit our area. Then the next problem is to find a good location for these stations, because if you put a station in the middle of the city, it will have a lot of noise. If you put it on a soft sediment, it will have a lot of noise. So the best should be to put it somewhere quiet and dig it into the ground or put it on a hard rock. So this always limits our availability of the places where we can put the station. Or the other case would be, let's say you want to use some very cheap instruments which still can record earthquakes, and you can buy a lot of them, and then you're not so limited. You can put them in many places. So
also the instrument, they have some which are cheap and some which cost.
Sorry, what?
I was saying the instruments.
Yes.
So it means they have some cheap instruments and also expensive instruments.
Yeah, of course. I mean, let's say there is as I said, for a professional use, we want to have those very expensive because they're much more, you know,
efficient.
They can record earthquakes at high frequencies. They can record earthquakes at very low frequencies. They can record very strong ground motion and all these things. But let's say some cheap instruments. So these are normally temporary stations. They cannot record very long period ground motion. So they are kind of useless for let's say tomography studies. Then maybe if a strong earthquake happens, the signal will be, I mean, the shaking will be too strong for the station to record it, and so on. But, you know, let's say a lot of times when a large earthquake happens, people go there and install these temporal stations because you expect smaller earthquakes than there, and more stations you have, even if they are not so good, more information we will have. So it's always good to, you know, kind of.
Okay, thank you.
So in the best case scenario, what you should do is put professional seismic stations in some area, let's say every 20 kilometers, and then between them you should put low-cost devices. This would be some very nice thing, but you know, the problem is always money here. And then, okay, since you already asked, just a second, let me open one website. Let me find it. I can maybe, if we will have time, I can also show you a PowerPoint that I just had last week for there was a school at ICTP on citizen science, so I can also talk about this. So, okay, let me share the screen now. So these are, you see, this is a map of currently running very low-cost seismic stations that even scientists use. Otherwise, this is a citizen science project. So just for hobby people, those that want to look at the earthquakes as a hobby. But let's say we can zoom here on Nepal. They installed many stations. I think 25 stations here in the country of Nepal, while the professional ones are not many more. So with this project, this is some PhD student did this, and this really works very nice. And then let's see, in Africa, in Ghana, you don't have any Raspberry Shake in Ghana.
Yes, you install it.
Yeah, no, you can buy it and put it in your house, and
sure.
it will show up here if you have internet, of course. But then, let's see. Now the volcano is erupting here in Iceland, so you can maybe there are some earthquake. You see here, this is real-time data. So maybe maybe these are earthquakes. Who knows? So these are low-cost devices. Such a device costs, let's say, around 400 euros, while some professional devices will be also like 10,000 euros or something like this. So you see, it's very, very big difference. You can actually see this Raspberry Shake if you go to Fab Lab at ICTP. You see there is one installed there. And you can ask the people there in the lab to show you if you're interested. Or maybe when the corona is slightly out of, when it gets better, I can come to ICTP and show you this, because currently I cannot go over the border. Okay, so let's go back to the So you see PowerPoint?
Yes, yes.
Okay, so let's continue. Okay, so another source of errors for earthquakes is the velocity model that we have for one specific area. So let's say here in this picture, so this is depth, and this is kilometer per second for P waves in blue and S waves in red. So you can see that there is this global velocity model called ESP-91. So this is this line with big jumps. And for the location of earthquakes, we can use this velocity model. Or the newer studies, of course, give a much more detailed. So this blue, which is not so discontinuous, this one, this is done by some lady from Italy. She did it for our area, and you can see there are quite some differences between the global one and the one for the region. So what this means is that, let's say, if you use the this one, ESP-91 model, let's say if your earthquake happens at depth of 40 kilometers, maybe your velocity model, because of these jumps, will wrongly locate earthquakes. So instead of 40 kilometers, it will put it here at 35, while if you would use the more continuous velocity model, you would get much better location and depth estimate. It would still, of course, contain errors, but smaller ones. The problem here is that we do not know the composition of the crust so good that, you know, with new methods, you can always make these models better. And then a new method comes and you can make it better, and you get more observations and you can make it better. But, you know, we have to work with what we got. So the next error for the earthquake location is the phases of earthquakes. It comes from the wrong detection or imprecise picking of the phases. So when the earthquake happened, you can, I will talk about this later a bit more, but what you can do is you can pick the phases by hand, but the problem is that, you know, who has time for this? It takes too much time when there is a lot of earthquakes. If there is one earthquake per day, no problem, but if you have a, let's say, some aftershock sequence with tens of thousands of earthquakes, you really cannot do this. Then we have automatic phase pickers that we will look later at them, but you will see they are not always very accurate. Unless, let's say, in last few years, there is a big jump in machine learning methods for phase picking, and this actually what I tested in last months. It's very, very good. The problem is that in general, you need to have quite a powerful computer, and you need to have a really huge data set to train your computer how to pick the phases. What it turned out actually is that earthquakes around the world are quite similar to each another one. So we can use, let's say, test training data from California and detect earthquakes in Italy. It's possible, and it works actually very good. So this is kind of, in next few years, I guess this will be a very common way to pick the phases. So let's say in this example, you know, you can decide to put a P wave arrival here or maybe here. So there is a small time difference. And normally when we use these hand-picked time arrivals or even computer-picked time arrivals, we need to specify some uncertainty. So let's say 0.01 second error is always present in the phase picking. So then finally, when we have, you know, when we detect and locate our earthquakes, we might get a plot like this. So imagine this red line is a fault, and these are earthquakes that we located around the fault. Now, you know, if our velocity model and stations and everything are very good, then maybe we can locate these earthquakes better and we get this kind of picture, or maybe we get this kind of picture or this one. It really depends on the geology in that area. But just, you know, you should know that normally in a majority of studies, you will see something like this. So a map that is mapped, a fault that is mapped on the surface, and the earthquakes that are distributed around the fault. So we have to live with this. So this is an active fault. Okay, so now let's look also how the manual phase picking and automatic phase picking, what are the differences, so where the error can come from. So the STA over LTA, what's written here, this is a short for short time average over long time average. So this basically means that we take long window here on the signal and a short signal here. You will see this later on the pictures, and then we calculate the average. And you will see that in this example, this computer method STA over LTA picked the face here, while I would put it actually here, because this is the first change. Why computer put it here? Because of the way how the signal is filtered. If I would use some different filtering band, then this menu automatically picked face would be somewhere else. Okay, I will talk about this later. Now just we are going fast through this introductory part. Then we also have this cross-correlation detection of earthquakes, which we'll talk more about later. So we can, if we are able to if we are able to pick a face very precisely on one earthquake, and if we find earthquake which is very similar, the waveform looks very similar, then it means this second earthquake happened almost in the same place. And we can use this cross-correlation technique to automatically try to adjust one waveform to the other and get a relative time correction for the phase peak of the second earthquake. So let's say original earthquake is in black. The second earthquake we found and has an identical waveform is in red, but because we did not correctly pick the phase, we can cross-correlate them, and at the highest cross-correlation value, so 98%, we see that we need to shift our red signal for 0.013 seconds to the right, and we get this black one and green one, which are completely identical. But more on this also later. Now, then there is this is actually a comparison. This is the work that I did for my PhD. There was a large aftershock sequence that happened, and automatically using the STA-LTA detector, I was able to detect these blue earthquakes. So this was, I think, 76 small earthquakes. And then when I looked at the raw waveforms, I was able to locate 1,500 more with very low magnitudes. And then in the last step, I made so-called templates out of these automatically detected earthquakes, and ran this cross-correlation detection that we will talk about later. And I was able to detect even more these very, very small earthquakes. So now this automatic part is very fast. As soon as the sequence is over, you can run this, and in a matter of minutes, or let's say hours, depends on how much data you have, you can get these detections. It gives you some information, but you see that a lot is lost. To do this, it took me, I don't know, 2 months to go through all the data. So it's really time consuming, and I don't think you should do this. But then to detect these very, very small ones that everyone missed before, this is again just few hours of computational work. So try to not do the manual picking of the phases if not needed. Okay, so now let's look at the some of these methods. So the STA-LTA detection that I told you before. This is one of the most simple algorithms for phase detection and picking, and of course it's also one of the quickest. To detect an earthquake, to detect an arriving phase, so let's say a P phase, we have to look at our data within a certain time window and constantly calculate the ratio between this. So, these are the two time windows. The short time window is this red one, and the long time window is this blue one. So what we do now, we take this time window and calculate the ratio between them. And then we go another step further and another step further and so on. So, this ratio will be stable, and when we get to the part where our phase starts, the ratio will change, and this is how the computer is able to identify the phase. Normally at these STA-LTA detectors are used at the local seismic institutions for continuous monitoring of the area, or let's say for early warning systems. And this runs on the real-time data. If you are interested in different earthquakes, let's say local one, regional one, and teleseismic earthquakes, you need to always run differently configured this STA-LTA algorithm. Otherwise, you will not be able to detect all the earthquakes. So let's say if you are interested in these three, you need to have three sets of algorithms set. So this is how it looks like. This is the raw recording, and this is the ratio between the long time average and short time average and long time average. So you see, as soon as the earthquake happens, the ratio jumps, and then it goes back down. And another aftershocks here that you cannot even see, but because we are calculating ratio, we can detect it, and it shows up. And another one, and here another one, and another one. So these red lines and blue lines that you see here, this is the so-called trigger, on or off. So this means that when our signal overcomes this trigger on that you can see here, it will say, okay, earthquake happened. And when it reaches the off, the blue line, it says, okay, the earthquake stopped. So you see this spike here, maybe this is some small earthquake, but because it did not go over this red line, it's not treated as one. This is quite okay if you are not interested in very, very small earthquakes, because very small earthquakes are often hidden in the noise. So you cannot use this methodology to detect them. So you can see here, this is example of one station and few earthquakes. So we can see the red line is detected P arrival for this earthquake. So you see this is the P window, P wave starts here, and this is S wave, and then it stops. So you see this one was picked quite nice, but then we have a small aftershock here, and you can see that the P should be here. It did not get detected, but it got triggered on S. This means that if we would put this earthquake, this P arrival in calculation, the location of this earthquake would be wrong, because it would use S arrival, not P arrival. And let's say here, this is one very, very small earthquake that you can see that the methodology did not even detect. This is, again, visible here. This kind of bigger earthquake was nicely detected, P and S arrival, while these aftershocks here and this one were not. But we can, we can look in the frequency. This is this earthquake, and you see that we have another two small windows here and here, which are these earthquakes that were missed here. Okay, then let's say another interesting algorithm to detect earthquakes is so-called kurtosis for the detection of earthquakes. It works slightly different. So you can see this is the raw recording, filtered raw recording, and this is the kurtosis of the signal. And you can see that when the P arrival starts, this jumps very high, and when the S arrival comes, it also changes. So what is this? So the logic of this kurtosis is quite simple. This is an average of the standardized data raised to the 4th power. Here is the equation, yes. So this means that any standardized value that is less than 1 will not contribute to the kurtosis. And this will be, yes, because this is close to 0. Basically, okay, let's not go into details here, but basically, if we look at the kurtosis of the signal, you can see that this is this recording here is this red one. So this is noise, and we can see that distribution of noise is kind of normal. but as soon as the earthquake happened, the distribution is not normal. It becomes, this is very high. So these are the scales of the kurtosis that you see here, and this is a way to detect the earthquake. But this is not so used, but let's say just to see different examples. And then we have this machine learning, face picking. As I said, it's very nice, but requires huge amounts of high quality process data sets to detect earthquakes and relatively powerful hardware. So let's say in this case, they used almost 780,000 earthquakes for the training. So this means that you need to have an area which is very with many small earthquakes to test it. Otherwise, you cannot do much. But as I said, luckily you can use training data from California on, let's say, Ghana, and try to detect something there. But it will not. Maybe it's better to add also earthquakes from Ghana to the training. And you can see here the raw recording, the STA, LTA function. So you see, okay, these earthquakes are detected, and then this is probability from the machine learning for P green and pink S. You see it works very good. And in some cases, let's say here where the signal is not so nice, the P and S are still very nicely picked. Okay, then let's talk about this match filter detection algorithm. So this is the one that I said before. This is when you have earthquakes that look similar, so they happen almost at the same place. Their waveform will be almost identical. And for this, we use this so-called match filter detection algorithm. So basically, what we do, we take one earthquake and we use it as a template. And then we go through our continuous data set, sample by sample with this template, and calculate the cross-correlation value between the template and between the continuous data set. And where the cross-correlation value is very high because the two signals are almost identical, this is where we can declare our earthquake. So normally how this is done to not, this is basically, it's quite intensive thing for the computer because we are dealing with huge number of data. So let's say if this is our original earthquake at 200 hertz per second, we download this data to, let's say, 20 hertz because we still don't lose too much information. And let's say, depending on the distance of these earthquakes, but let's say they are close by, we can broadband filter this data between 2 and 8 hertz. So it looks like this now. And then we cut small windows around P arrival and S arrival. And then we use these two small time windows as a template to scan through the data. Okay, this is then how our template looks like. So basically the correlation is calculated in this way. I mean, it's basically just comparing two signals one to the other. Actually, in seismology is even slightly easier because it's not an image, but just a time series. And then this is how this cross correlation will look like. So this is the raw recording. And this is after the scan. You see that we get these spikes. These spikes are where the cross correlation value is very high. And this red line is some threshold that we said that if the cross correlation value is above some preset threshold, then this is our detection. So we see here some foreshocks and then the aftershock sequence. To visualize this, in red, this is our template, and in black, it's our continuous waveforms. And you see that this is the high cross correlation value when they look very similar, at least at some point. Or maybe here, the blue is template, and you can see that cross correlation here, it goes up, but not enough. So basically this is probably just a noise. Here the cross correlation is slightly higher, so it reaches our red line. So this is called the detection. And here it's very high cross correlation value. You see that the template and detected earthquake are almost identical. Okay, this is, I already told you that we can use this then as a relative time picker, so we can do these small shifts. Yes, okay, this is it. Now let's look at how we can locate the earthquake when we have the phase arrivals. One approach to solve this problem of earthquake location is using the order of first arrival times to locate the event. I think that it's important to mention here that you can also detect an earthquake, locate an earthquake using a single station, but in this case, then you cannot really resolve the depth of the event, except if you can really identify depth phases, but this is really, really hard work. So with one station you could calculate the distance with looking at P and S arrival times, and you could then calculate the azimuth from where the signal is coming from, and this is how you would get an approximate location. Okay, so at the beginning, I showed you the picture with 3 stations and those circles around them. So this is the easiest method. But then we also have this very early, very simple method called Vadati diagram. So this is this diagram that you can see here. Even today, this is still used to check if the picked phases on some station from some earthquake are strange. So basically what this means is that if we have different stations and all detect the same P wave, this should align like this. So this is the time difference between S minus P, and this is the arrival of P time. And this is how we would get origin time, where this cuts our axis, and if they are aligned, then our phase peaks are very nice. But if some station would, jump very high, then this would mean that either, I don't know, maybe there is something wrong with the station, the timing is not okay, or that we or our computer completely missed the P arrival. Okay, then in the case of an earthquake, the source location is defined by the hypocenter of the earthquake. So this is X, Y, and Z coordinate. And then we have the fourth unknown, which is the origin time of the earthquake. So the hypocenter is commonly considered to be a physical location of the initiation of the rupture. So let's say if we have a small earthquake, the hypocenter is where the earthquake stopped. But if we have a very large earthquake, then the hypocenter is where the rupture started, but then the rupture propagated, tens, even hundreds kilometers away. So to get a location of the earthquake, we have, very simple equation is here. Of course, this is just very simplified, but basically we have an equation with 4 unknowns. So what we need to solve this is 4 arrival times from at least 3 stations. So this would be P or S arrival times. So we have, let's say we have n number of stations, then we have n observations, and this means that we will also have n equations. So this will be overdetermined system. And this has to be solved in a way that and the easiest way to solve this kind of problem is to calculate the residual or misfit at each station. So these are the residuals. Basically, what this means is that the easiest way to understand this is to take an area and make a grid inside of this area, right? And then for each of these grid, we can calculate what would be the observed time of the P arrival from that area, and what is the actual P that we get on picked face. And if these two are very small, if the residual is very small, then this means that this grid node is, probable location for the earthquake. But you can read some papers on the earthquake location. You will see that this gets very, very complicated fast, and today's methods are quite complex. So we can try to minimize these problems, this residual. So one method is to use the least square approach. This is most common measure of misfit or residual, since it leads to a simple form of the equations in the minimization problems. The real problems, however, are more complex. So this misfit can get out of hand quite fast. So what we can do, we can calculate the misfit by summing the absolute residuals, but this will again make everything a bit more complex. So the root mean square can be also used to get these residuals. This is normally calculated for every earthquake, this RMS. So you have some idea how this is well located or not. So yes, when we have this RMS, we take a grid, and for each grid node we check the RMS, and where we get the minimum, this is where we should put our earthquake. The problem becomes, it becomes problematic when we have many minimums, not just one. So the algorithms should also consider the P and S arrival times to say, okay, maybe this area with very low residual is too far because the P and S on these stations would not agree then with proposed location. And what we normally do is, so we take initial grid, and then when we find a small, when we find a minimum within this grid, within this minimum, we can create another grid, and then another and another, and so on. This can be done in few steps. So even though the computers are getting stronger and stronger, these seismic source locations are still mainly done by other methods than grid search. So these methods are based on linearizing the inversion problem. And the first step is to make a guess where the earthquake happened and what is its origin time. And then, so we can use this, let's say, we say, okay, maybe earthquake happened around the station which is closest, which has the lowest P, S minus P. And then we can use this as a starting location. And then we search the area around. This is not, this is quite boring. So maybe it's not so important because every software that you will use has a different algorithms and they all give more or less the same location. So maybe it's not so important, but what it is important, I think, at least for me, are these relocated earthquakes. So by some classic location methodologies, we get so-called absolute location of the earthquake. There is to know a good, to obtain a very good absolute location of the earthquake, we need to know the velocity model of the Earth. We need to have all the information, all the errors, on all the errors from our reading of the data, timings of the GPS. So there is many things that can go wrong. So what we do with the relative location is that we try to minimize these errors, especially the one from the velocity model. But the problem here is that we can only use relative locations for earthquakes that happen very close by to some very well recorded earthquake. So this would look something like this. So if we have earthquake 1 here and earthquake 2 here, if the distance between them is very small compared to the distance between the stations, then we can try to calculate the so-called double difference algorithm. We can use the double difference algorithm that will remove these errors that I told you about before. So this will now give us, if our earthquake 1 is very well located, but earthquake 2 is not very well located, we can use this to kind of find the distance between these two earthquakes and give the second event a better location by knowing this, double difference residual. So here are some equations that, oh well, if you read this paper by Waldhauser, you will understand this a bit better. But basically, this checks the observed travel times and calculated travel times, like all the methods, and try to calculate the double difference for between these two earthquakes. In when look at the earthquakes, this is a grid search method location. You see that these earthquakes are located on a grid, so it gives you some strange idea how this sequence looks like. And this is by using some other method. This is the same sequence, and you can see that before we had a line like this, now we have line like this, and I trust this better because I know there is a fault in this way. This is also, you can see a big clustering of events, let's say here and here, while here you don't see this. This method is from this double difference. You can also see that while here everything is clustered around the depth of 15 kilometers, this is because of the velocity model, because it has a jump at 15 kilometers. Here, this is slightly more spread because I used some different velocity model for that area. But you can see some structures maybe that could even be a fault plane. Okay, so let's now look at some examples of the match filter detection. There are some very nice papers where they used this methodology to observe, let's say, transient deformation within a system. So most likely, you know, the L'Aquila earthquake. This happened in 2009 in central Italy. It destroyed the city of L'Aquila with around 300 people that died. And what happened there is that there was a long foreshock sequence, but just by looking at the catalog available at the time, they were not able to see so many of them. So this is a comparison using match filter detection. You can see they were able to detect many more these small earthquakes. And by having so many of these small earthquakes, they also were able to observe migration of seismicity towards the hypocenter of the main shock. And looking at this migration and some GPS stations later, today we know that this L'Aquila earthquake was preceded by a so-called slow slip event detected by both migration of seismicity and GPS stations. So if we would know how to calculate these things in real time, we could maybe know that there is something preparing a large earthquake. We did similar study for the 2016 earthquakes. Our paper came out last year, and we also showed that same thing happened before the central Italy earthquakes in 2016. So there is a migration of seismicity and slow slip detected from GPS stations, and then big earthquakes that happened. Another interesting example of using this match filter is this volcanic eruption. So what you see here, these are spectrograms of the station close to a volcano. And what they saw is this strange signal. They call this, how they call this, screaming or something like this. So they did not understand what this signal is, but you can see that here you have some earthquakes, but then the earthquakes stop and you have this continuous signal. So what they did, they took these earthquakes, ran the match filter, and they actually figure out that this is not a continuous signal, but it's made out of very small, very similar earthquakes. And it actually turned out that this was migration of the magma from the chamber beneath the volcano towards the summit, and then here the explosion. Okay, here is one also example of this match filter detection of earthquakes. We can identify different earthquakes in some fault system, and then we use them as templates and try to find earthquakes that look very similar. And we can see that sometimes there is kind of migration from one side of the earthquake from the faults to the other, and so on. Okay, so I will not say anything about this. This is it. Do you have any questions? Oh, you fell asleep, huh?
So we are here. Okay, my camera is okay.
So what time is it now? 12:20. Okay, so tomorrow I will show you this, how to pick the phases and how to calculate the location of the earthquake. I will show you with actual examples, so you get a slight feeling for this, because this theory, I know it's not really interesting. So we will go hands-on tomorrow.
Okay, thank you very much.
So if no one has any questions, let's finish here today. And we can Zoom. You can now. We can try to install the OpSpy for you. So I mean, if everyone else is interested, we can.
Yes, we